Before we can discuss the other limits on the operating altitude of an aeroplane, it is important to discuss the aeroplane stalling. When the speed of the aeroplane is reduced, in order to still produce enough lift to balance weight, the angle of attack must increase. However, below a certain speed, the angle of attack on the wing is such that the flow of air over the wing starts to separate from the boundary layer, producing turbulent airflow. The separation point fluctuates back and forth along the wing, making strong eddies in the turbulent airflow. These strong eddies buffet the elevators or tailplane. This phenomena is called low-speed buffet. Flying below this speed will dramatically decrease the lift and a full stall ensues. For any given weight and configuration, the aeroplane will always stall at the same indicated airspeed. But the equivalent Mach number for the low-speed buffet and stall increases with altitude, as illustrated in this simplistic diagram. The Mach number for the low-speed buffet is abbreviated to m-min. A similar buffet can occur at high speed. At very high speeds, close to the speed of sound, the compressibility of the air ahead of the aeroplane leads to the formation of shock waves or high-pressure waves. These shock waves create a disturbance to the flow of air over the wing, causing it to separate and create turbulent eddies. Similarly to the low-speed buffet, these eddies will buffet the elevator. This phenomena is called high-speed buffet, and the Mach number for the high-speed buffet decreases with altitude. Flying faster than this speed may cause a high-speed shock stall, and in an aeroplane whose wings are not designed to overcome such effects, this could be quite catastrophic. The Mach number for the high-speed buffet decreases with altitude as shown. This speed is commonly abbreviated to m-max. Taking into account both the Mach number for low-speed and high-speed buffet, it means that there are two Mach numbers, below and above which the aeroplane is unable to fly. This speed range between the Mach number for the low-speed and high-speed buffet is called the buffet margin. The important point to understand is that the margin between the low-speed and high-speed buffet decreases with altitude. Notice that at this altitude, the low-speed and high-speed buffets are coincident. It is impossible to fly higher than this altitude. Flying slower or faster than this speed shown will stall the aeroplane. In fact, even maneuvering the aeroplane will initiate a stall because maneuvering the aeroplane will increase the effective weight and increase the stall speed. This altitude is called the aerodynamic ceiling or coffin corner. To prevent aeroplanes from operating too close to this altitude, an operational limit is set below this altitude. Notice that a 1.3 g maneuver moves the buffet speed lines to this position. Notice now, the Mach number for the low-speed and high-speed buffet are coincident at a lower altitude. This lower altitude is called the 1.3 g buffet limit altitude, or maneuver ceiling, and it is usually about 4,000 to 6,000 feet below the aerodynamic ceiling. Adding these two altitudes onto the graph shown earlier helps you to see how these different altitudes and ceilings relate to one another. When the aircraft gets close to the destination airfield, it will reach a point which marks the beginning of the descent. This is called the top of descent. You may remember that in order to initiate the descent, firstly, the thrust must be reduced, and then the nose is lowered to get weight to act forwards to balance the drag. The balance of forces ensures that a constant speed can be maintained during the descent. The descent profile is almost the reverse of the climb profile. The climb profile for a typical 737 is initially flown at 250 knots, then at 10,000 feet this changes to 280 knots, and then at the crossover altitude, Mach 0.74 is maintained. The descent is flown initially at 0.74 Mach. and then at the crossover altitude the speed is kept constant at 280 knots. But when the aircraft reaches 10,000 feet, no more than 250 knots must be flown. Shown on screen are the characteristics of that descent, so you can see what happens to the gradient and rate of descent throughout the descent profile. If at any point air traffic control asks the pilot to expedite the descent, then the only action taken by the pilots would be to deploy the speed brakes. This increases the drag, which must be balanced by more weight apparent thrust. Therefore, the nose is lowered, which increases both the angle and rate of descent as per the instruction of air traffic control. The next descent to consider is the descent characteristic following either depressurization or engine failure.